this F is Newton, I am talking about Newton's second law, F vector equal dp dt. dp is the linear momentum vector. So what exactly this F is?
So, sir, they say it is, somebody says it's just force, somebody says total force on a particle, somebody says external force, and somebody says resultant force vector, sum of all external forces, resultant force.
So all answers are partially correct in the sense that a force can be instantaneous or acting for a very long time, and it may be constant in magnitude, changing in direction, and or else changing in magnitude as well as direction, whatever it could be. So F stands for resultant of all forces which act on a particle of mass m at a given instant. At a given instant. I repeat again, at a given instant. Why is it so? That is my next question. Why am I emphasizing on the phrase at a given instant, resultant of all forces acting on a particle at a given instant? It is not instance. Instance is example. I said instant. A tiny dot speck of time. Instant.
So, sir, it
What?
is impulse. What they say it is
No,
either.
no. Nothing to do with impulse. It is as simple as that. What is our equation? F is dp dt. dp dt, of course, is differential coefficient of linear momentum vector with time. And what exactly is a meaning of differential coefficient? It is the instantaneous rate of change of linear momentum with respect to time. If the right hand side is instantaneous, even the left hand side need to be instantaneous. So therefore F is simply the resultant of all forces acting on a particle of mass m at a given instant. I believe my point is clear to everybody. What I want to emphasize is physics is simple if one looks very hard on the mathematical equations which represent some physical fact. So this is the Newton's second law. And P, of course, linear momentum, as we all know, is mass times velocity vector. And in Newtonian mechanics, mass is constant. It is not relativity. So mass can come outside, and we have F equal in A. A is dv dt, which is acceleration. And dv dt again is instantaneous rate of change of velocity with respect to time. So if velocity is changing with time, then it is simply instantaneous rate of change, which of course is, I'm uttering nothing new. This is what is known from differential calculus. Now, what I want to emphasize is that all fundamental laws in physics, which we have learned at the very basic level, for example, Kirchhoff's law, Kirchhoff's second law for network analysis. I just make an allusion to that. Suppose we have a network and there are several batteries in the network, EMFs are given. So algebraic sum of EMFs equal algebraic sum of potential drops. IRs, I current, are the resistance. This is what Kirchhoff's law is. Now, my question is, what does here algebraic sum of EMF E stand for? Is it average EMF? If we have a varying EMF, alternating EMF, is it instantaneous EMF? Is it average EMF? Is it RMS EMF? So answer is, as I said, fundamental laws, and this particular Kirchhoff's law is an energy conservation law. So the EMF is instantaneous. Similarly, current also is instantaneous. All fundamental laws refer to instantaneous situation. Now, to determine how a particle would move under the action of a set of forces, I have the Newton's law. I can very nicely get from this law velocity, position vector, etc. at all time. So situation is totally deterministic. With a single or a few particle, there wouldn't be much of a problem. But if there are a large number of particles, and we want to know the dynamics of this large number of particles, then application, how large could it be in a volume of, let's say, 1 centimeter cube? In a solid, we have as many as 10 to the power 20 molecules packed. So if we have so many particles all packed together and we want their dynamics and apply Newton's second law, so probably we shall have to wait for another 50 years when quantum computers come into the market and people start using it. Probably such a problem can, people probably can attempt to solve such a problem. Right now, this is an insurmountable problem. So Newton's law attacks particle dynamics problem where many particles are involved in a very local specific fashion. In principle, a law is perfect, nothing to, there is no lacuna, no flaw, but problem associated is insurmountable. So I brand Newton's law application as a local kind of application. On the other hand, if somehow we can go over to, rather than force is a vector, rather than force, we go to energy, kinetic energy, potential energy, all such things, wherein collective motion of the particle could be dealt with easily. Such a situation, I refer to as global situation. And the approaches that I am going to talk about today is, the first one is the Euler Lagrange equation, or Lagrangian formulation of mechanics. This could be treated as a kind of global approach because this will not involve vector like force. For vectors are complicated to deal with. It will involve energy. So Euler Lagrange, before we discuss Euler Lagrange equation, by the way, we all know that the Euler and Lagrange, all these people were the very famous mathematicians of 18th century, and their contribution to mathematics is enormous. So if I now look at the first slide, we consider, say, a system of n particles with holonomic constraints. Constraints are important. Particles are not spread out in a continuum. Suppose a particle is supposed to move on the surface of a sphere, then and sphere has radius a, then if origin is the center of the sphere, the coordinates of the particle x and y, uh, uh, and the third coordinate, of course, is z, they would satisfy equation x square plus y square plus z square equal a square, where a is the radius. So you have put in a constraint, a restriction on the movement of the particle. So a restriction, of course, is expressed in terms of an equation, and a restriction or a constraint uh, bearing an equation is called holonomic, and a restriction which could be expressed in terms of an inequation, that is in terms of an inequality, or greater than or greater than equal to or less than equal to, is called non-holonomic constraint. So suppose we have n particles with k holonomic constraints, and suppose Fj is resultant force on each particle, and uh, resultant force, the virtual work due to each of the forces would be F dot Fj dot drj, which is known to everybody. That work is expressed in terms of dot product of force. And in this case, since we are saying virtual work, so delta Rj is virtual displacement. And sum over all j's, a sum over all j's in this case should be zero. Reason being, the resultant force on each particle, uh, unless there are external forces from outside, resultant force on the system would be zero, and displacement also is virtual. So the total work is zero. Now we split this force Fj, the force on jth particle, into two parts. Resultant of all external forces, suppose external forces we bring in, are resultant of applied forces and forces of constraint. A few words about constraint. For example, particles are encaged in a cubical box. So particles, while moving, will strike the wall, and there would be change in momentum of the particle. The rate of change of momentum, of course, is the measure of the force, the constraint force which the wall exerts on the particle. Or particles are, suppose, or bodies are moving on a surface, of course, is not smooth, so there would be a force of friction, solid friction, which would oppose the motion, and of course there would be a force on the floor which will be in the same direction as motion, as we know from Newton's third law, that to every action there is equal and opposite reaction. Action reaction, they act on different bodies. And therefore, herein I have not considered internal forces, that is, force acting on ith particle due to jth particle. For the entire assembly of these n particles, such internal forces, force of interaction between the ith and jth particle, ith particle will exert a force on jth particle, jth particle in turn will exert a force in the opposite direction on ith particle. So they will cancel each other. So the internal forces are not there. So we have, for virtual displacement delta Rj, Fj a dot delta Rj plus Cj dot delta Rj, and sum is taken over all j's, and this is equal 0. We always choose constraint forces such that, because virtual displacement is something which we are producing off the cup. So I may always take constraint forces and virtual displacement, they are perpendicular to each other. So the constraint forces, the forces of constraint go away from the equation, and you have a resultant of external forces A dot delta Rj equals 0. So this is called principle of virtual work. It could be stated as the necessary sufficient condition for a system to be equilibrium. That virtual work of applied forces vanishes for all virtual displacement. You might say, where has the concept of virtual work come in? Well, uh, now, as we understand, our vacuum is not really a vacuum. Particles pop in and out of vacuum for very small time. So these are called virtual particles. Similarly, virtual work is, of course, not something which will pop out from nowhere like a popcorn, but it is just an imagination that, okay, if I give some kind of displacement which actually has not taken place, but imagined that if some displacement had taken place, system of particle in equilibrium, where the forces of external forces are on the jth particle is, let's say, fj a, total work done on the system would be 0 if the system has to remain in equilibrium. Displacement in calculating the work is assumed to be virtual. We had, in fact, at our +2 level or even BSc level, in our honors as well as BSc program level, we have seen that the condition of equilibrium is that total resultant force acting on a particle or a body should be 0, and total torque should also be 0. So that statement and this statement for equilibrium is not very different. Only out there you had total force 0, total torque 0. You are not talking now in Lagrangian formulation in terms of force. You simply have assumed a kind of imagined displacement, and you are saying with such imagined displacement, total work should be 0 if the system is in equilibrium. With this, we go to the second slide. So, can you project the second slide now?
Yes, sir.
Second slide. Yeah. So, I go to the fact that in general case, n particles may not be in equilibrium. The Newton's law, just now I have stated, gives me total force equal dpj, force on jth particle, of course, dpj dt. And this implies, because the mass being constant in Newtonian mechanics, so mass of the jth particle comes out with this virtual displacement thing. The condition or statement of Newton's law comes out to be if JA minus mj rj double dot, rj double dot, whole of it, take dot product taken with virtual displacement equals 0. And of course, here the work done by the forces of constraint have been assumed to be constraints, forces of constraint have been assumed to be perpendicular to displacement. So this equation 1, which I have written down, is nothing but a simply a different form of writing Newton's second law with virtual displacement part thrown in, and this is called the Lagrangian principle. Next, next we introduce the generalized coordinates. What are they? Suppose I have n particles, they are constrained to move in three-dimensional space, so they have 3n coordinates to specify their location. And suppose there are k number of constraint equations, then total number of independent coordinates will be 3n minus k, and these total number of independent coordinates, 3n minus k independent coordinates, I denote by q1, q2, q3, and so on, q3 and k minus k, and position vector of an each particle will be in a non-equilibrium situation. Forces, when external forces act, of course there is non-equilibrium situation. So in a non-equilibrium situation, the position coordinate is a function of these generalized coordinates q1, q2, and so on, q3 and minus k, and of course the time. So one obtains the velocity uj, which is rj dot drj dt, that is, from the chain rule, one can write as I had written drj dqk dqk dt, sum over all k's. K, of course, is running from 1 to 3 and minus k, or j running from 1 to 3 and minus k, and delta rj dt. And the virtual displacement similarly could be written as drj dqi dqi sum over all I, that is the virtual I summed over index unsummed, index which in the summoned, which has been left out, is j. So virtual displacement delta r will be associated with unsummed index j. So delta rj is defined in this fashion. Our idea, yes.
Sir, there are too many questions. May I read one or two to you? Otherwise, in the end, we'll have 100 questions.
Sure.
Sir, one is could you explain significance of virtual work?
As I right at the beginning said, Lagrangian, we are right now giving idea of Lagrangian formulation of particle dynamics. We already, all of us, our students, they have at a lower level studied particle dynamics through Newtonian approach. Newtonian approach required putting in, knowing what are the forces acting on the particle, and take resultant of all forces, instantaneous resultant of all forces, write it as mass times acceleration dv dt of the particle, integrate with respect to time, you get velocity, further integrate, you get displacement, and if you know what are the initial conditions, so at all times to come, what would be the trajectory of the particle, such things are predictable. So Newtonian approach is totally deterministic. But the problem arises when we have very large number of particles, and which is what we have in a solid of, as I say, 1 cc volume. We may have as many as 10 to the power 20 atoms, particles, and we want to study dynamics of such system. So in that case, approach with Newton's law, one has to wait for 50 to 100 years to get through this kind of problem. Uh, alternative approach is at not going through force route, to going through energy route. Now going in through energy route entails introduction of work, because work anyway, work done on a system is is potential energy of the system, all that. So it entails defining some kind of work. Now, work for defining, if the system is in equilibrium, there is no mass displacement of the system. A particle is in equilibrium, no displacement of particle. But I can always think of, as I said, vacuum. I think we assume, used to assume earlier, particle physicists and quantum field theorists earlier, well, vacuum is a tranquil sea, but it is not. As we now know that all kinds of particles, they pop in, pop out. Similarly, I can assume that even though there is no perceivable displacement of a particle, I imagine that there is some displacement, and which I call virtual displacement. And if I define work with the aid of that virtual displacement, I call it as virtual work. And why I started with work, I explained, because my approach has to be an energy related approach, not force related approach to dynamics, because force related approach will have lot of complication. Energy related approach will be simpler. I think I have answered the question.
Yes. Sir, there is a question. Can you explain the force of constraints with an example?
Oh yes, as I said, solid-solid friction. Solid-solid friction, when a body moves over a solid surface, one has studied it at school level, 9th, 10th level. There is, due to the craggy nature of the surface, irregularities, there would be a force holding a body back, and in turn, so motion will be opposed, motion of the body, and in turn there would be a force on the floor which will be in the same direction as the motion. So this is friction force. This is a constraint, force of constraint. And another example I also have given, that body, a system of particle is contained in a say box. The wall, when particles moving, colliding with wall, there is change in momentum. Rate of change of momentum will be the force that the wall exerts on the particle. So these are constraint forces. Had wall constraint been not there, there would never have been such force.
Sir, is virtual displacement something like tunneling of electron in a tunnel semiconductor where there is displacement without covering any path?
No. Display tunneling, of course, is a very different phenomenon, which has no counterpart in classical approach. This is classical mechanics. So tunneling is a totally quantum mechanical phenomenon, wherein particle with energy less than the height of the potential barrier can move through. And now people have also found that the tunneling is not instantaneous. So what answer to this question is, don't draw comparison between the macro world and micro world, that is quantum world. Macro world has its own rules, micro world has different rules.
Sir, Adrija asks, virtual displacement and work only works on bodies on equilibrium. Is it so?
No, work can, you can imagine displacement on a body which is not even in equilibrium. Where is the problem? I don't see any problem. Why should there be any problem? Like the second slide, which is open, in the general case, I just have written the first line. When the system of n particles is not in equilibrium, I have, I'm still applying virtual displacement and writing down certain things, certain formulas, equation 1a, equation 2, and all that. So it is obvious that virtual displacement in non-equilibrium situation is also applicable.
Sir, Prashant asks, virtual displacement means there is no displacement actually. If there is no displacement, then work done will be zero. It's already clear. Then why are we bringing the concept of virtual work?
Well, let the boy understand, saying, okay, my body temperature is at the moment, say 98°F. That is an average. The temperature is fluctuating, blood pressure fluctuating, hemoglobin count fluctuating, sugar fluctuating, slight fluctuation. So displacement is not there at, at the level of his judgment. But at microscopic level, there could be displacement. As I have been, I just twice or thrice I said, a particle all of a sudden coming popping out of vacuum. Otherwise, one thinks particle vacuum as tranquil sea, but is it really a tranquil sea? It is not. The particles keep popping in, popping out of the sea, right? Similarly, displacement to his eyes, the system of particles not getting in equilibrium and everything. But there could be, at a much smaller scale, could be displacement. So this is why we imagine a kind of displacement which we call virtual.
So Kritika says, is there a practical world application of principle of virtual work?
Practical work, because principle of virtual work will lead me to, just now I will show, will lead me to Euler Lagrange equation. And whatever result you get for particle dynamics applying Newton's law, you will get the same result with Euler Lagrange equation. In fact, beyond that, we shall also discuss Hamilton's principle. We shall discuss also Hamiltonian approach. All of them are alternative approaches to attack the problem of particle dynamics. And advantage relative to Newton's law is that Newton's law, I keep repeating, requires concentration of force. Then these approaches require energy. So Newton's law, in my own part, lingua franca, I call Newton's law is something local because it gets down to each and every force. On the other hand, the Lagrangian Hamiltonian formulation, they refer to energy, and energy is globalized, energy of a system of particle. So it is Lagrangian and Hamiltonian formulation which we are going to study is our global approach, and principle of virtual work is the foundation stone of is one of the most fundamental requirement to develop this idea.
Sir, there is another question. Sir, can you please explain equation number 1a and what is k in the generalized coordinates?
K is the number of constraint equations. You see, as I said, okay, a particle is to move on a sphere. If particle can move even, go even inside the sphere, to locate its position, I require three coordinates, x, y, z. I think everyone understands it. On the other hand, if I put in a restriction that particle or whatever is can travel only along the surface of the only on the surface of the sphere, that means the coordinates have to satisfy somehow the equation of the sphere, which is x square with center at the origin, as a origin at the center, x square plus y square plus z square equal a square. So that becomes the one constraint equation, and requirement of in a non in a situation where there is no constraint, there are three coordinates required to specify location of particle. With one constraint equation, the number of independent coordinates required to locate position of particle will reduce to two. The better coordinates are r theta, something like that, r theta phi, the spherical polar coordinates, so maybe r theta. So point is, k here is number of constraint equations, and which has to be subtracted to 3n, 3n being the number of coordinates, n being the number of particles, to give us number of totally independent coordinates. And in the equation 1a, actually the participant is right. I should not have taken k and k getting confused. I should have taken some other index rather than k. I should have taken something like, let us say, lambda, zeta, or whatever. I should have written, because k anyway is going to get summed over. So you must read it as uj equal rj dot equal sum over all lambdas, which all lambdas drj dq lambda q lambda q dot lambda plus del rj del t. So that what is this lambda? Lambda is number of what? Independent coordinates.
Sir,
That is 1, 2, 3, 4, and so on up to 3n minus k. Writing k has created, in fact, probably confusion in the mind of the participant. I should have used index, lambda, sigma, or any such thing, and that lambda, sigma spans over number of independent coordinates 1, 2, 3, 4, and so on up to 3n minus k, where k is number of constraint or equations which are imposed on the system of n particles. Am I clear now?
yes. Sir, is Lagrangian just a tool to solve equations, or it tells us
Yeah.
something more than that of Newton's law?
No. Lagrangian is just is an object, is a quantity which is involved in Euler-Lagrange equation. It is equal kinetic energy minus potential energy involved in Euler-Lagrange equation, which is a differential equation we solve and we get the particle dynamics. Like in Newton's law also, we solve and we get the particle dynamics. But here, as I said, we are dealing with energy.
Yes. Sir, one last question which I will take right now as you continue is that Neha asks, sir, I didn't get what it means exactly that there is no displacement but we imagine there is displacement in the case of virtual displacement. So it is not clear.
No displacement from our point of view, but there could be small displacement because in our universe, there is at micro level at least. Of course, you may say why you are referring to micro level. You are teaching, you are talking about classical picture and micro level, that is, you're going to quantum mechanics, but uh, forget the that issue at this moment. But at micro level, there is never ceasing motion, and in fact, this never ceasing motion is the offshoot of our uncertainty principle. Well, I will not go further. Anyway, this never ceasing motion always gives rise to slight fluctuation in every conceivable quantity. So when I say there is no displacement, well, the fluctuations I am not able to see, but there will be definitely fluctuations, though our mathematical construct which I am presenting is not taking care of those fluctuations. Here, the displacement which I have put in, I have never called it as a fluctuating displacement or something. I called it virtual because within the ambit of classical approach, such fluctuations could not be taken into account.
Yeah,
So,
sir, please continue your
yeah,
lecture. Otherwise, I think
yeah,
we'll spend 1 hour
yeah,
only
yeah,
answering
yeah,
questions.
yeah. I now go to the third equation. In fact, sorry, third slide, and refer to the term we have in the D'Alembertian equation, which is a variant of Newton's law. The first term was fj dot drj, which I now write as f dot drj delta qj, and I define some quantity qi as fj delta rj q upon delta q. Q, say the index j is summed over, so you have qi, and this is called generalized force. Generalized force, one may notice, may not have precisely the dimension of force, because q, which is generalized coordinate, had this been only a displacement, r and r in the numerator, a displacement in the denominator, dimensionally would have cancelled each other, and q would have had dimension of force. So neither generalized coordinates will have dimension of position, or L as they say, or nor generalized force need to have dimension of force, which is mlt to the power -2. And then I said that the velocity u, del uj, del qi dot meaning derivative with respect to time, that of course will be delta rj, delta qi, very easy to see. So this derivative ddt of delta rj, delta q will ultimately come out to be delta uj, delta q. This is all mathematical description. I don't think much of. Why? Because delta rj, delta t will be rj dot, and delta q is already there. Rj dot is nothing but uj. So one gets finally the right hand side as delta uj, delta q. Mathematical manipulations. We go to the fourth slide, and then in the fourth slide, please go to the fourth slide. Okay, here I take the second term of the D'Alembert's principle or law. Second term involved mj rj double dot delta rj. which is you are dividing by delta Q, multiplying by delta Q, so to say. So we obtain the left-hand side equal derivative with respect to time of this quantity minus the quantity that I have written down. By doing the differentiation, one can check that this is all right. And then noting that Rj dot is uj, I have arrived at the equation below the blue bar, and finally I write in the left hand side of the equation, let's say 4, which is mj rj double dot dot product with delta rj summed over all rj equal this quantity. This is all mathematical manipulation. If one does it nicely, sitting down coolly, one will easily get. And we now go to the fifth slide, where fifth slide, please. Fifth slide. Fifth slide, please. I'm sorry, it is fifth. Yeah, fifth. So upon identifying half mi ui half mj uj square with kinetic energy, the D'Alembert's principle becomes sigma j ddt of del dt. T is kinetic energy. Qi dt dt dqi. I think I need a little blow up. It is the qi dot, it should have been, then minus dt dqi minus qi delta qi. For this is true, this summation is true for any the kind of displacement delta qi of generalized coordinate. Therefore summand has to be 0. If the summand is 0, one is led to ddt of del t, capital T, del qi dot. Mind you, it is del qi dot, del qi dot, meaning derivative with respect to time, minus del t del qi. This is equal qi, where I is from again 1, 2, 3 and minus k. So this is D'Alembert principle in terms of the generalized coordinates. I'm recalling that the force is gradient of some scalar potential. One knows this definition. So generalized force qi could be written as minus del phi del qi, and this generalized scalar potential phi supposedly does not depend on generalized velocity. We are in our everyday calculation hardly come across any problem where the potential is dependent on velocity. Therefore, I can rewrite this equation 5 in this form: d dt of d delta t minus phi dqi minus delta t, qi dot, I'm sorry, because the font is too small, may not be visible, but if you blow it up, you will find that in the denominator you have dqi dot minus dt d minus phi del qi equals 0, and Lagrangian function we define as T minus phi, kinetic energy minus potential energy. So this leads me to this differential equation, equation 8, which is our celebrated Euler-Lagrange equation. And the equation have the same form for any set of generalized function and unknown forces of constraints, which do not, forces of constraint could be any. They may be known or unknown, but our formulation in terms of Lagrangian is independent of the presence of forces of constraint. Therefore, this is a big advantage over Newtonian approach. In Newtonian approach, one cannot forgo the constraint forces. Supposing I ask you, okay, forget many body problem, you want to do a few body problem. Uh, well, what would you do from your concept of whatever you've learned in school? You would say we go over to center of mass system of few body. But one pertinent question still remains, is what are the forces of constraint? So you may ask whoever has questioned you, give me the forces of constraints as well, if you are applying Newton's law. But if you are applying this differential equation, Euler-Lagrange equation, to solve the problem, you need not know what are the forces of constraint. They don't appear in our formulation, unlike the Newtonian formulation of dynamics. This is greatest advantage of Lagrangian formulation over Newtonian formulation. I think I am clear to everybody. Hello, I think I'm clear to everybody.
Sir, the students say, yes, sir, it is clear.
It is clear. Very good. Then, if that
Sir,
is
just
so,
a second. Sir, just a second. One announcement for the students. After 10 minutes or so, when sir allows, we shall give the attendance link. And I would request you to kindly focus on your lecture, please, and not on the chat box. Okay. The moment your eyes are on the PPT and your eyes are on the speaker and your ear is working for the speaker, how is it that it is going on the chat box? How is it possible that you can read and write the chat box and listen to sir, who is teaching wonderfully well, and his PPT, which might not be to your liking because you're the new and the technologically advanced generation? Keep your senses in the correct direction. Listen to the speaker, watch the PPT, and take your eyes off from the chat box. Write only when the sir asks, may I know whether I'm clear or not? Otherwise, your chat box will be muted forever. Yeah. Thank you so much, sir. Please continue.
okay. Okay. Now, I would like to do a few problems. In fact, later on, I may give a huge number of problems as assignment uh, to show how this Lagrangian formulation can solve problems on particle dynamics. So I have taken a very simple system. Uh, I have a spring of spring constant K firmly attached to the floor at the point P, and there is a table with a hole in it, and X and Y axes have been shown, and we have a thread with to which is connected to the spring, of course, and a mass m is attached to it. So what happens is this. Just read the problem from the point P. Spring factor is K, of course. Mass m is on a smooth horizontal plane. The point P, to which the lower end of the spring is rigidly attached, so placed that when mass m is at the hole, the given spring is unstretched. When mass m is on the hole, spring is unstretched. I think you are understanding this word. Show the angular momentum of the particle is conserved for an arbitrary displacement of the particle, meaning you have stretched the spring and let the mass move some distance in the horizontal table itself as shown. So in the second part, you have to show the path of this mass will be in general an ellipse. Or could be as a special case circle as well, with origin as the center O. And we are to show that the
Sir, are we on the sixth slide? Are we on the sixth slide or the fifth?
we are on the sixth slide.
Yeah, sir, so probably you did not say it. Yeah,
Oh,
thank you.
sorry,
Now we
sorry,
have the
sorry,
sixth slide.
sorry,
Sir, you have to be
sorry,
very
sorry.
careful because these students start writing 20 times that it is next slide.
Oh,
So when
okay,
you
okay, okay.
change, please write. Otherwise, they bombard the
Okay,
chat box with it.
I forgot, I forgot. I'm so sorry. We are on the sixth slide. We are, I repeat again, we are doing a problem where in the problem we have a spring of spring factor K, which is fixed to the floor at the point P, and then there is a hole on the table through which a mass M is attached to the spring through a thread, and suppose when the spring is unstretched, the mass M was right at the hole itself of the table, but when the spring gets stretched you are stretching the spring by pulling the mass is on the table surface. I am to show that the if I let the mass go, path will be elliptical one. The table surface is assumed to be smooth, no friction. So path will be a path of mass small m will be elliptical one. I am to show, and I am also to show that the angular momentum of this particle will be a conserved quantity, angular momentum conservation. So now let me ask everybody, what is angular momentum of a particle? How do you define angular momentum of a particle? Of a particle, I am saying. We are not discussing rigid body problem. So therefore, I never would refer to any rigid body. I would say always a particle. So angular momentum of a particle, how is it defined? Uh, well, if one, I have not written it, but can explain verbally. Suppose I have origin O, I have a particle at some point with position vector R, and particle has linear momentum P, then angular momentum of the particle about the point O is defined as R cross P. It is cross product of R and linear momentum vector P. That means angular momentum vector will be perpendicular to the plane determined by the position vector R and the linear momentum vector P. I think all of us know, all of you know, that cross product AB is perpendicular to the frame, perpendicular to the plane determined by the vectors A and B. So this angular momentum is R cross P, or its magnitude is MBR, or uh, if you write V for rotational motion as of course V is vector, angular velocity is also a vector, so V is omega cross R. But forgetting the vectorial nature, I can write magnitude of angular momentum as mr square omega. For V we write omega R, so mr square omega. Now this system is actually the moving body in the system is the mass m, and this has 2 degrees of freedom, which are because mass is constrained to move on the surface of the table, so it has 2 degrees of freedom r theta. Kinetic energy can be written down easily as half m r dot square. R dot, you understand, is dr dt, and this is radial velocity, and transverse velocity is r theta dot, and you have square of r theta dot r square theta dot square. This is easy to understand. I have resolved the velocity of the particle into radial component and the transverse component. And force acting on the particle on the mass m also is in horizontal direction, and that is due to the spring. Spring has got stretched through a factor how much? Sorry, say factor delta r or dr, then force will be spring factor, magnitude of the force will be spring factor multiplied by dr, and virtual work will be, as I have written down, k dr multiplied by r displacement. And so you have the kinetic energy, you have the work. Work gives me negative of work done is potential energy change for a conservative force, and spring force is a conservative force. I think all of you know it. For a non-conservative force, of course, potential energy cannot be defined. In fact, for a non-conservative force, we have total mechanical energy change is to be considered. Anyway, so we have spring force as a conservative force, and work done by it is minus kr dr, and therefore uh, the potential energy change for this situation would be delta U equal simply kr dr, and then we apply the Euler Lagrange equation. What was the equation? If one goes back to the fifth slide, please go back to the fifth slide and look at fifth slide, please. Fifth slide. Uh, yeah, look at the equation 8. This is Euler Lagrange equation. You have L is kinetic energy minus potential energy, Q is generalized coordinate, which in this case, in the problem, there are two generalized coordinates, r and theta, and then you have in the equation dl dq dot and overall time derivative of that, then minus dl dq, that is equal 0. This is your equation 8. So since q's here are the generalized coordinate, and coming back to our slide number 6, please come back to slide number 6. We have two generalized coordinates r and theta. Therefore, equation 8, which is Euler Lagrange equation, which is simple differentiation. If you apply that, you get two equations which I have written down: mr double dot minus mr theta dot square equal minus kr, and I also have mr square theta dot ddt equals 0. These two equations are obtained, uh, uh, as I said, taking q, one of the q's to be r and the other q to be theta. R and theta are our here two generalized coordinates. Now, if I look at the second equation, I have ddt of mr square theta dot equals 0. So mr square theta dot is a constant, and this is precisely our angular momentum. So this is conserved. Now, to show that the motion trajectory will be in general an ellipse, we go to the seventh slide. So going to the seventh slide, one sees that one has adopted, it is convenient to go to Cartesian coordinates, kinetic energy half m x dot square plus y dot square, and work done minus kr dot dr is written as minus k r dot dr. Sorry, r dot is missing. I'm so sorry. R, it should have been r dot dr minus k x dx plus y dy. Why? Because r is in two-dimensional situation, xi yj, delta r, delta xi, delta yj. So upon taking dot product, you get x dx plus y dy, and once again I would have Euler Lagrange equation, a differential equation of second order first degree in two generalized coordinates x and y as mx double dot equal minus kx and my double dot minus ky equal minus ky. Now, what do these two differential equations individually correspond to? What kind of physical system? Let me ask you. Please tell me what kind of physical system these two differential individually, each of them correspond to. No idea. These are second order differential equation of first degree. You all realize that? Hello?
Hello, yes, sir, we can listen you.
These are mx double dot equal to minus kx, my double dot equal minus ky. Both of them are the second order differential equation of first degree, right? What physical system do they correspond to? Each of them. Yes, tell me. No, no response. That is, I would say, not quite satisfactory.
Sir, we can hear you.
Yeah, yeah. But, what I'm saying is, what equation, what physical system these two equations, say one of the equations, or both of them individually correspond to?
Sir, on YouTube, students are answering SHM.
Oh, very good, very good. Absolutely right. Absolutely right. These are the equations of SHM, simple harmonic motion. You see, undergraduate level, up to undergraduate level, your physics starts with SHM and ends with SHM. So if you cannot identify the differential equation of SHM, that of course is somewhat it is not a satisfactory situation. Anyway, so they represent, these two equations obviously represent two simple harmonic oscillations of same frequency or same periodicity at right angles to each other, because they are in x and y direction. If I say so, I think everybody now would agree with me. Everybody now would agree with me? No.
Yes, sir, they are responding. Everybody agrees.
Okay, so if that is that, then this would, if amplitude same, will correspond, but the path will be a circle combining the two SHMs. Path will be a circle, and if the amplitude is different, it would be in general ellipse. So the so path of the mass in general will be an ellipse. This is how it is proved. I think I am clear now, clear to everybody.
Yes, sir. Yes, sir. They are responding on the YouTube as well as here also.
Okay, very good. Then we go to problem number 2 in the same slide. How to solve simple pendulum problem by this Lagrangian approach. See, Lagrangian approach requires how many steps? Or let me recall, because if you are not very thorough with basics, you will never be able to understand nuances of higher physics.
Excuse me, sir. Sir, you are on mute.
S-
Sir, you are on mute.
Sir? Hello?
Now you are able to hear me?
Yes, sir. Yes, sir.
It gets disturbed. Okay. Now it is clear. All right.
Yes, sir. Now we are able to hear you.
Yeah, it is all right now?
Yes, sir.
Okay.
Yes, sir.
So what I am asking actually is very simple question. If one wants to do some problem, a school level problem, wherein one has to apply Newton's law, some dynamics of a body, right? Forces are given, one wants to know what is position, what is mass, and all tension, mention, all such things. So, what are the steps one takes to solve such Newton's law based problems? The steps one takes, let me not waste time. Probably students have never realized what steps they take, or probably have realized. Number one is show all forces acting on the system, forces, because Newton's law is force based. So all forces applying Newton's third law, action reaction law. And second step is split system into subsystems and apply second law to each of the subsystems. And third step is equations obtained applying second law to be solved for unknowns. So similarly, if I ask now to solve, because this kind of problem will be asked in their examination, whichever examination the student take.
Sir, you are on mute. Sir? Sir, you are on mute.
Okay. So now,
Sir, again it is mute.
now it must be all right.
Yes, sir. Yes, sir.
So what I would say is identify the first step is identification of generalized coordinates, because your Euler-Lagrange equation application will involve if there is one generalized coordinate, there would be only one equation. If there are two generalized coordinates, two equations, and so on. So identification of generalized coordinates is necessary. Second is get the derivatives. Sorry. Second is get the L, that is kinetic energy minus potential energy. Get the Lagrangian L, which is kinetic energy minus potential energy in terms of the generalized coordinates. So first two steps are clear. Third step will be set up Euler-Lagrange equation in terms of the generalized coordinates of the problem. And the fourth step is solve the differential equation thus obtained for the unknowns. So Lagrangian approach of solving dynamics problem involves four steps. Are these four steps clear?
Yes, sir. They are replying yes.
Sir, you are on mute again, sir. Sir, you are on mute again.
Right. I think there is some, I don't know what kind of problem. Anyway, Newton's law, sorry. Simple pendulum problem is the simplest problem, and we take this problem now and show how to solve it. We have solved it by applying Newton's law. We now show how to solve it by applying Lagrange's approach, or applying Euler-Lagrange equation. One sees, well, there are these.
Sir, you are on mute. Just a minute, sir.
Okay, again mute. I don't know why it is happening.
Yes, sir. We even don't know.
Sir, this is some technical problem. It also happens because of many network issues. And I would like the viewers to understand that there are several parameters that are going into this particular webinar, which includes connectivity and network issues and program handling and so on. If one is ready to learn, one can always wait for a second or so.
Yeah. Now I will keep an eye on this icon. If it gets mute, then I'll unmute it. Anyway, so my task is to identify the generalized coordinates, which, since the pendulum bob is moving in two-dimensional plane, I shall have r theta or xy. There are two such generalized coordinates. Say r theta. Kinetic energy can be easily written down as I have written, your half m r dot square, r square theta dot square, and well, potential energy will be how much? I have not written it down. In fact, one can write it down very easily. Suppose the pendulum bob is in the situation which is shown in the figure, then, and length is r. So if I...
Sir, again you are on mute.
Sir, again you are muted.
Okay. So
Yeah,
if
now
I
we can
wish
hear
to,
you.
if I wish to calculate potential energy, I need to show a zero potential energy line. So a zero potential energy line could be chosen as per my will. But in a given problem, if I choose my zero potential energy line to be something, then in the same problem, I cannot change it. But in a different problem, you can take some other line as zero potential energy line. So if I take our zero potential energy line to be a horizontal line coinciding with the steady position, mean position of the pendulum bob, a horizontal line coinciding with the mean position of the pendulum bob, then at an angular displacement theta, I think, and suppose mass of the pendulum bob is m, then it will be mgr into 1 minus cos theta. I think I don't need to explain that to anybody. Everyone understands why it should be that. Because potential energy, gravitational potential energy is mgh, mgh. So mg you are writing, and for h you are writing r whole multiplied by 1 minus cos theta. That is the height it has gone up to in the present displaced position. So kinetic energy and potential energy could always be written down easily, and then Lagrangian equation yields me.
Sir, you're muted again.
Yeah, mr double dot minus mr theta dot square equal radial force, and also mr square theta double dot 2mr r dot theta.
So could you please unmute? Sir?
Slide. We go to 8th slide, right? I think it is clear. Yeah. In the 8th slide, fr and f theta are components. Here r remains fixed. Thus, we may consider the second equation. Second equation is what? Mr square. What was second equation? Mr square theta double dot r remains constant, so second term becomes 0, equal the tangential force. So going over to the second equation, I get mr square theta dot equal minus.
Sir, please unmute yourself. Could you please unmute? Yes.
Yeah.
Sir, I think there is some technical problem at your end today because your network is not is making you mute.
Yeah,
again and
my
again.
network is playing truant, it seems.
Yeah, it's not a problem. It's not a problem, sir. Then probably we will wind up your session earlier today, so that we can continue when it is running more stable, because the students are very restive and they start.
They will get restive. So let me finish this as.
Yes, sir. You stop at a comfortable place and then we will continue with the next.
We have from second equation mr square theta dot equal minus mgr sine theta, and for theta much smaller than unity, sine theta is nearly equal theta. So this leads me to a usual so simple pendulum equation, theta double dot plus g by r theta equals 0, or which gives me time period as 2 pi square root of r by g. Now with this we go to the 9th slide, where actually go to the 10th slide, please. Go to the 10th slide, please. Yeah, one can see an Atwood's machine. One knows what Atwood's machine is. There is a pulley is fixed, and string and they are one mass is going up, the other one is going down, and one needs to calculate the acceleration of the masses. So this is the problem. And in the 9th slide, go to the 9th slide, please. I have just written that down. There is an Atwood's machine shown in figure which comprises of two masses M1 and M2 connected by a string of length L which is passing over a pulley of radius A, and pulley has, now pulley is not massless. You are assuming pulley has moment of inertia I. So that will have a lot of bearing. And string is massless and inextensible. And pulley is, I want to show that acceleration of the system is given by M1 minus M2 G whole divided by M1 plus M2 I by A square. Well, the problem I believe is clear to everybody. Problem I believe is clear to everybody.
Yes, sir. They are replying yes.
Okay, very good. So we go back to our 10th slide, wherein we have the Atwood's machine, and I have the pulley of massive pulley. I know how to do this problem with application of the within the framework of how to solve a rigid body problem. We know how to attack the problem through that method. Here the method to be adopted is different. The method is Lagrangian approach. To apply the Lagrangian approach, I need to get the kinetic energy and potential energy. So I have assumed the masses M1, M2 are at distance, the horizontal line passing through the center of the pulley. M2 is at distance x, and therefore M1 is at distance L being length of this string, L minus x, which is x2, the distance of the mass from the dashed line, and that x2 is L minus x minus pi a.
Sir, you are on mute.
Yeah. I know. I'm keeping an eye. Now we have how many generalized coordinates? We have, in fact, two masses. So there are 6 generalized coordinates. And how many constraints are there? There are 4 of them which prevent the motion in y and z direction. And 5th one is that x1 plus x2 should equal pi a plus pi a should equal L. So there are 5 constraint equations, 6 coordinates to locate masses, 3 for M1, 3 for M2, total 6, and usme 4 of the coordinates are redundant because we are not considering motion in y and z direction, and 5th one is because you have assumed string inextensible, so x1 plus x2 plus pi a equal L, constant. So there are 5 restrictions and 6 minus 5, 1. So there has to be only one generalized coordinate. As I said, first step is the identification of generalized coordinates. So I shall have only one Euler Lagrange equation. In terms of the generalized coordinate x, I think I am clear to everybody.
Yes,
Is this
sir.
point
Students are responding. Yes, sir.
okay? Very good. Then kinetic energy of the system half m1 x dot square, half m2 also x dot square, because derivative of x anyway, and rotational kinetic energy is half I omega square. Why have I written omega as x dot upon a? Can someone answer this question? Why have I written omega? Because rotational kinetic energy also needs to be considered. The pulley has mass and it has its moment of inertia I, isn't it? Through an axis passing through center of mass, moment of inertia I will be mass of the pulley m times k square, where k is the radius of gyration. So half I omega square will be the rotational kinetic energy of the pulley, and for omega I have written in the slide x dot upon a. Why have I written so? Can someone answer this? On what basis I have written so?
Sir, students are replying angle equal to arc by radius.
No, no.
Then
We
theta
have
is the
not.
angular velocity.
Yes.
Omega equal to V by R.
Omega equal is not. V's are omega fine, but some physical restriction I am looking at. What is the physical condition or restriction or some physics which makes us write omega as x dot a? What is x dot, by the way? What does it? What do our students understand by x dot? Let me ask that question. What is x dot? Velocity of
X
what?
dot will be the velocity of the surface of the pulley.
Velocity, first thing, x dot is the
Velocity.
instantaneous velocity of the masses, right? I think I am clear to everybody. And obviously that of the string. Now, if the string does not slip over pulley, the groove of the pulley, then the linear velocity of the pulley corresponding to the angular velocity, which is omega a, and the velocity of the string x dot should be equal. Is explanation clear? Is it clear?
Yes, sir. This is clear. Yes, sir.
If the string.
So some students are asking if you could repeat it once more.
If the string is not to slip on the pulley, then string velocity and linear velocity corresponding to angular velocity omega of the pulley, which is omega a, they should be equal. If the two velocities do not match, string will slip over the pulley. I think my point is clear. I think my point is clear.
Yes, sir, they are saying it is clear now.
It is clear.
Yes.
So in order that there is no rotation, there is no slipping of string while rotation of the pulley taking place, I should have x dot or omega into a equal x dot, or omega is x dot upon a. Is that right? I think now everybody is understanding why
Yes, sir, they are saying they are now
omega
understanding.
is x dot upon a. So what I want to emphasize is, unless one understands little physics of very little systems which are taught probably at the school level, one will not be able to uh, make a big headway in physics. Reason is, at every level, when you will be on your own in the research work, no one to help you out, all these basics which have entered into your bloodstream can only help you. No one else will help you. So getting basics right is very important for learning physics. And how to get it right? Well, to read very good books. In fact, uh, there are a lot many, for example, Resnick, Halliday Walker, for example, Tipler. These are the basics. Okay, now coming to the problem, I need to write the potential energy. As I said, to write potential energy, I need to fix the line of zero potential energy. I had taken that dashed line, horizontal line, which is passing through the center of the pulley, as the line of zero potential energy. So therefore, masses out there, the M1, M2, they are at depth x and L minus x minus pi a. So potential energy V I have written as minus m1gx minus m2gl minus pi a minus x. And as I said, the first step is to identify a generalized coordinate, and you had found there is only one generalized coordinate x. So Euler-Lagrange equation will be d dt of dl x dot minus dl dx equals 0, and you have your L as t minus v, which had been defined. If you solve this equation immediately, you will get x double dot as m1 minus m2 into g divided by m1 plus m2 plus I by a square. So I believe the tips to how to apply Euler-Lagrange equation to solve problems, small problems of mechanics. You will not get very big complicated problem. Small is clear to everybody. There are only 3 to 4 steps. Identification of the generalized coordinates, writing down the kinetic energy and potential energy, and then writing down the Lagrangian, and then the third step is writing Euler-Lagrange equations in terms of generalized coordinates, and of course solving the differential equations. You get whatever quantity they have asked you to solve for in the problem. So with this, we now go to Lagrangian of a, and we have a little time. I think, madam, I am to leave at 7 o'clock, isn't it? Hello?
Yes, sir.
Yes, sir, I think that
We
will
have
be
to
good.
take
Yes,
a
sir.
break also.
Okay. So I would be able to finish the
Sir, you have got muted actually.
Yeah, muted. I know. Please go to the 13th slide.
Sir, if this problem is persisting, then Dr. Geetanjali is already in. You can wind off after a slide and then she can start, or you can switch off your video. Then probably it will the network will function better. So if you just switch off your video and
Acha.
speak only,
Okay.
let the mic be on. Then
Okay. Yeah. Okay. So I believe now things are all right. We have to calculate Lagrangian of a charged particle, and Lagrangian meaning kinetic energy minus potential energy. Now, I probably other madam has started electromagnetics, and people have studied EM field theory, electromagnetic field theory. They must have now, they are familiar with the vector and scalar potential. So scalar potential is denoted by phi, it is a scalar, and vector potential is denoted by A. Lagrangian I am to show for a charged particle moving in EM field with a velocity v equal, if the mass of particle is m, I am to show half mv square minus q phi. Q is the charge of the particle, q plus q times a dot v. Now, I'm sure all of us know that magnetic field B is related to the vector potential by the formula B is curl of A. And why B is curl of A? Because Gauss's theorem in magnetostatics tells us that divergence of B is 0 and divergence of curl of a vector is 0. So B has to be curl of some vector. That is your A. That everyone knows. And also one can show that electrostatic field E is negative gradient of scalar potential, electrostatic potential, but electric field per se will be E equal gradient of scalar potential and time derivative of vector potential. So these are well known. And they are invariant, the scalar and vector potentials are invariant under gauge transformation. That is, if you change phi to phi dash equal phi minus d phi d psi dt, where psi is another scalar potential, or a to a dash equal a plus grad of psi, then where psi is an arbitrary function of coordinate and time, then nothing happens, because as we all know that say divergence, this is gradient, so you have curl of gradient of a scalar function is 0. All these are well-known formula in vector calculus. So we now start with the Lorentz force, which we are all familiar with. A charge Q moving an electromagnetic field E and B. Of course, E and B here treated as separate entities. They are not separate. In fact, they are the two different two components, let us say, of electromagnetic field tensor, which is tensor of second rank and all that. We can see that later. So F is QE plus V cross B. This is Lorentz force. B is curl of vector potential A, and electric field is gradient of scalar potential phi and time derivative of vector potential A. We put in all this, these two in the expression for the Lorentz force, and then write down the x component of it, which is 12.2 12.37 and 12.38. In fact, let me share with you why such odd equation number, because I have taken all this from my own book. No plagiarism. It may be a self-plagiarism, but anyway, it is my book, so I can take the liberty. That is why this kind of numbers or this kind of equation number appears. So we go to now, after writing the x component, we go to which? We go to 14th slide. 14th slide.
Sir,
So,
sir, it is
yeah.
10 minutes to 7 and you have been going on continuously for 1 hour 50 minutes. So, sir, we have to now give a break to the students.
You please give, but can I finish this slide and then give? Then it will be over. Or you want break right away, and whichever way you want.
Sir, as you say, we will today's question answer session, we will paste it on a doc file or Excel file and sir pass it on to you. And today we have to finish fluid dynamics also.
Okay, very good, very good.
For somebody else.
Okay, then I would start.
Here. Yeah.
I would start off with the same Lagrangian of charge particle in electromagnetic field.
So that's your decision.
I will do that again. Okay, so I end my discourse at this point. I hope everybody had understood what I had spoken about. Shall I end now? Hello?
Yes, sir. The students need to fill up their attendance and we need to give them a break before fluid dynamics has to start.
Then I'm just leaving. I'm sorry, but I also have to leave. There is urgent work coming up. Can I leave now?
So we shall continue with where you have left today and in your next session. Presently, we would like to thank you a lot for your
wonderful. That's all right. That's all right. Not every day. Now thanking every day is not required. In fact, I am enjoying more than anybody else. I think that you had done a great service to me, giving this opportunity to interact with students.
Okay, thank you so much, sir. Thank you indeed. We have to thank. It is written. It is written in our very, very respected text, both in Hindu.
Yeah. So okay, I leave now.
Air or a beautiful enlightening lecture, we must keep thanking. So sir, thank you again, and words are never enough. Thank you so much, sir.
Right, sir. Thank you.
So over to Dr. Thiranjita and Dr. Neetu. We would now, so this attendance link.
So the attendance link has been shared. Dear participants, please now fill the attendance form, and this is a break for 10 minutes.
No, five
minutes,
because Dr. Geetanjali Sethi is already here. So 5 minutes for you for them to fill up the attendance form. And sir, if you would like to stay, it would be nice. However, if you would like to leave, it's all up to you. It's your decision.
Would be, there is something urgent which I need to attend.
Yes, sir. Yes, sir. It's perfectly okay. Thank you so much, sir.
Right.
Welcome all. Oh, yeah, so Geetanjali ma'am is there. Welcome, Geetanjali ma'am.
Yeah, thank you. I'm here.
Punita ma'am, are you there? Punita ma'am?
Yeah, I'm here.
Yeah, yes, ma'am. Punita ma'am, I request you to please welcome Geetanjali ma'am, and so that she should proceed with the
Yeah,
session.
everybody can, just a sec. Everybody can welcome our very dear Geetanjali Sethi. And she has started fluid dynamics with us yesterday. She is continuing with fluid dynamics today also, and with a wonderful style of teaching on the board. So Geetanjali has created a problem for other teachers that students want now whiteboard teaching by everybody, which I'm sorry to say and I must announce, not every teacher will write on the whiteboard, right? This is a webinar series arranged for the benefit of the students. And if your ears are sharp enough, you have to put up with a big band of teachers. And let me tell you, world famous teachers are scheduled to come here. World famous. I'm not talking about India famous. World famous lecturers are coming here. Geetanjali Sethi is no less a very, very ardent worker. She is herself pursuing 2 courses simultaneously to the lectures that she's giving to our students. She's doing a course with Ayuka. As I said, she has finished. She's ongoing with a refresher course, and she's doing a special course on optical interferometry. And hence is a lesson for you all students that whatever work is assigned to you, apart from that, you should be a continuous learner. Thank you, Geetanjali. Most welcome. Please continue with fluid dynamics. Yeah.
Thank you, ma'am. Thank you. Good evening, everyone. I would continue with my topic on fluid dynamics, and let's see how much I can cover today. I'll try to get to Navier-Stokes equation. If not today, then tomorrow. And yes, I got some emails which were asking for certain clarifications. I didn't answer them because some of them were related, some of the questions were actually related to what I'm going to teach today. And so you people should have patience. By the end of my lectures, I'll definitely answer everybody's email. I'm just waiting for you to go through the lectures. Maybe your answer, the answer to your question, you'll get during my lecture only. If anything remains unanswered, you'll definitely get the answer to that question over email, right? And I would again request people not to keep posting in the chat box because it is distracting for me. And I will definitely try to answer all questions during my lecture or else towards the end. If anything is left, again, for people who were not there, my email address is geetsethi@gmail.com. If I miss out your query, if I miss out your question, you can just email it to me over my email, right? But I'll answer your questions only after I have finished my course, right? And as I told you yesterday, the books that I'm following are Landau Lifshitz, Volume 6, which is a book on fluid dynamics, and Feynman lectures. Right? I'm going to go very slowly today because yesterday you got an overview, you got an idea about when and how we start applying fluid dynamics. Today we are going to do some mathematics, which is going to be slightly involving. I'm going to go very slowly. If you find anything that you don't understand, you can ask me in the chat, in the Q&A box. I'll try to answer it as and when possible. Right? So let me just review what we studied yesterday. What we found out yesterday was what we define as a fluid element. You know what we define as a fluid element. Fluid element is something which the size is such that it is much smaller than the actual volume at hand, the dimensions at hand, the dimension of your problem. For example, if you are looking at fluid in a container, then V naught is the volume of the container. Or if you are looking at your fluid is a gas which is in a room, then your V naught is the size of your room. And dV is a small volume element within this V naught, right? But it is sufficiently large to contain 10 raised to power 5 to 10 raised to power 6 particles of your fluid. right? So that's the definition of your fluid element. This is something that you should always remember, as I insisted yesterday, because you are so used to thinking in terms of kinetic theory that fluid element for you often becomes a single particle, right? But we are not looking at a single particle. We are looking at a finite volume, which is much smaller in comparison to the dimension of my problem, right? Then we had obtained two very important equations yesterday. First equation that we obtained was the continuity equation. Right? The continuity equation read as del rho by del t plus del dot rho v equal to 0, where I will remind you rho is a function of x, y, z and t in general, is the density of my fluid, and can you see this part of the board? Can somebody tell me if you can see this part of the board? Okay, and v is the velocity field, which is also a function of x, y, z and t, right? It is the average velocity defined within my fluid element, within my volume element that I am dealing with. And the second equation that we got yesterday was Euler equation, right? And the Euler equation, I will remind you, was nothing but the equation of motion of your fluid element, of this small volume element under consideration, and it read like this. And what is P? P is the pressure, which we had defined as force per unit area that was experienced by my volume element due to all the remaining fluid other than my fluid element, right? We had also written down the Euler equation in a very important form. In fact, that form is actually very important because I'm going to use that form today. And that form in which we had written down our Euler equation was in terms of the work done. Right? And that was del V by del T plus V dot del V equal to minus grad of W. Right? I'll remind you, how did we get this work done? Where did we get this work done from? We got this work done for the cases where my system is a non-viscous, a non-lossy system, and my process is an isentropic or an adiabatic process, so that the entropy doesn't change. And from there, we had written down Euler equation in terms of the work done. Right? So these were the two equations, the continuity equation and the Euler equation that we had yesterday. And then we had solved the Euler equation for a particular case. That particular case for which we had solved the Euler equation was a case of hydrostatic system. And we saw what do we mean by a hydrostatic system is a system for which velocity is 0. Right? That means the system is in mechanical equilibrium, right? And for such a system, we saw that pressure is only a function of Z, and so is the density. Right? Now, before I start working towards Navier-Stokes equation, there is one more simple example. So this was the first example where we looked at application of a hydrostatic system. And I showed you that an example of a hydrostatic system we worked out yesterday was Earth's atmosphere or if you have volume of a liquid or a fluid in a container, and that of stars, spherical stars, right? We wrote down, we obtained, we didn't solve exactly the Euler equation. We wrote down the final Euler equation. And I told you that if you are given the boundary conditions, then you can actually solve the Euler equation to obtain the density profile and hence other quantities which are, see, if you, once you know, see, you must understand, once you know the density, you know the velocity profile, you can find the density profile from the Euler equation. Once you know velocity and density, then there is something called equation of state that you have seen in thermodynamics, right? Then you can also find pressure. You can, like yesterday, for this simple case of hydrostatic equilibrium, we could actually see, that is the beauty of doing simple examples in physics. Like if you remember the case of hydrostatic equilibrium that we looked at yesterday, we actually completely solved the Euler equation and obtained the pressure profile. We got a solution for pressure and we obtained an expression for pressure. Then we applied the boundary condition and we could actually determine how will the pressure change for such a system as you go along. So this is nothing but solving your Euler equation. So now you know your pressure profile. If you know your equation of state, that is, you know what kind of a gas it is. For example, one equation of state that you dealt with in your thermodynamics case is an ideal gas equation, right? So suppose you were dealing with an ideal gas, you know what the equation of state is. Then you know your pressure, you know a relationship, you have one relationship between pressure and density, you know your equation of state, you can find all other thermodynamic properties of your system, right? So that is the whole idea. That's why it is important to do some simple examples like hydrostatic equilibrium and the kind of example that I'm going to do today to get a feel for what is really happening in my system in terms of physics, right? Okay, so this is the recap of what we did yesterday, right? I'll erase this. And I'm going to now solve it for a case which is next level than your hydrostatic case, is that for a steady flow. So now your fluid is not at rest, like in the case of hydrostatic system, but now your fluid is actually moving, but it is moving at a steady rate. So what does that mean? That means that V is a constant in time. It doesn't change with time, but is still a function of, you have to remember, is still a function of XYZ. You know, I will remind you, you call such quantities, you must have learned in your vector calculus course, vector fields, right? That is, you have a definition, you have a value of V at every point XYZ. So as points XYZ change, velocity changes, but velocity doesn't change with time. So that is what you understand by a steady flow, right? So now how do we translate this into mathematics? In terms of mathematics, this means that the partial derivative, time derivative, why partial? Because you remember I showed you yesterday that if you have a vector field like velocity, then the velocity vector field can change because it's a function of position also. As you move along the fluid element in time, see, that's what the second part of your equation that we had yesterday meant. So we saw yesterday that if I look at change in velocity with time, it was actually del V by del T plus V dot del of V. What do we really understand by this second term? What we really understand by this second term is, if you look at this change is with changing position. So as time is evolving, this is evolution of your velocity field with time. This is evolution of your velocity field at any particular location in time, right? So I told you that velocity field can change in two ways with time. One is as you move from one point to the other, and the other is you are sitting at the same point, but you are looking how things are evolving at the same point. Now, if the flow is steady and you keep concentrating at a particular point, nothing is going to change, right? So that's what I understand by a steady flow, and that's what translates into the fact that del V by del T is not going to change. This is at a particular point, at a particular x, y, z, right? But as you move along the fluid, things can change, right? Things can evolve. So if you look at this term, is this term that as you are moving, but as you move, time will definitely progress, right? So as you move along the fluid and you go to different locations, your velocity field can change, your value of velocity can change, right? So you must understand these small, simple mathematical things that you come across when you are doing mathematical analysis, right? Okay, so what are we going to look at? So for us, the case at hand today is hence where del V by del T is 0, right? Now, if you just think a little bit, you realize that in this case, if you go back and you look at your Euler equation, now your Euler equation will read now. Maybe I should write an intermediate step because there might be people who were not there. So my Euler equation, which I just wrote on the board before this, was what? It was del V by del T. So this is my actual Euler equation, general case, is V dot del V equal to minus grad of W, right? Then I told you that you can replace this term using an identity from vector calculus. And substitute this into my Euler equation. If you do that, then my Euler equation becomes, I will substitute for V dot del V in my Euler equation, and I get right. And now for the static case, for the steady flow case, not static case, for the steady flow case, this is 0. And hence I get half del V squared minus V cross del cross V equal to minus grad of W. I'll wait for a minute before I erase this. If somebody has asked a question that whether I can repeat how to write the Euler equation completely in terms of derivative of velocity, this is right here. The next step would just be taking a curl of both the sides. So when you will take a curl, the gradient terms are going to vanish because curl of a gradient is 0. So this is Justin's question. I did that yesterday, Justin. If you just look at this last equation and you can just take the curl of both the sides and you will get your Euler equation completely in terms of I'm going to talk about an example of steady flow in real world. That's what I'm going to do. This negative sign, this negative sign, somebody has asked about this negative sign. This negative sign we got yesterday in pressure term, right? This is because we are looking at pressure that's acting on the fluid due to remaining fluid. So this is a sign convention that we had defined. This is because everything else is surrounding my volume element and it's exerting an inward force. So that's why I had a negative sign here. We discussed it yesterday. Ma'am, how sign has got changed here? Nowhere the sign has changed, Bachan. I have not changed the sign anywhere. I have just, yesterday, I might have written this on this side, right? I would have put a 0 on the other side. The signs in the last step. Have I made a mistake? Oh, okay, yeah. Oh, true. So I have substituted for B dot del V as V cross, no, and okay, right. So I will have half del V square, okay, minus V, right, and thank you. So nice, perfect, right. So I agree. Thank you. A lot of people pointed that out. Wonderful. I just changed the sign throughout. That's perfect, right? Okay, so we have this equation. Now I don't need this equation. I'm just going to go back to the equation that I required. I'll just write now the equation that I need, right? And then start from there, right? Okay, so the equation that I have now is half del B square minus V cross. If there is a negative sign mistake, I'll just figure it out, right? Don't bother, don't worry about that. If there is a sign mistake, I'll just figure it out. It will give me, if I make a mistake in sign, I will just get a wrong sign somewhere and then I'll correct it. Don't worry, right? Okay, fine. So now I have my Euler, I'm certain about this equation. There is no mistake in this equation. This equation is perfectly correct. So if in between I might have made a sign mistake somewhere, we'll just try to figure that out soon. So don't worry about that sign somewhere. This equation is what I should get if I just keep all my signs correct, right? Okay, fine. So now for a steady case, del V by del T equal to 0, I have this equation, right? Now, before I go further ahead with this equation, there is something that I want you to understand. There's a term that we often use in fluid dynamics is what you call as a streamline, right? Now, there are ways to represent fields. You can represent fields in terms of gradients, divergence, and curls. You can represent fields in terms of fluxes. You can represent fields in terms of field lines, right? So the way, just like you define field lines in other things that you come across in physics, you also define what are called streamlines or stream field lines in fluid dynamics also, right? Now, what is a streamline? Streamline is something that gives me, that's actually a tangent Or rather, if I represent my field by a streamline, then a tangent to my streamline at any point actually gives me the direction of velocity of the fluid at that point. Right? So you represent the flow of a fluid by what is called a streamline, and at any point, if you want to represent the velocity of the fluid at that point, that is simply given by the tangent to the fluid line at that particular point. Right? Now, so if you just try to think about this definition of a fluid line, and you think of tangent at that point to represent the velocity field at that point. Now, what will be the tangent? So if I'm dealing with this in, let's say, 2 dimensions, right? So then I can write down the tangent to my field line as what? I can write down the tangent to my field line as dy by dx, right? And if that is the direction of the velocity vector at that point, then the slope of the field line, that is the slope of the tangent to the field line, is given by dy by dx, and that is also equal to, if you resolve your velocity vector at that point, will be equal to vy by vx, where vy and vx are components of your velocity vector at this particular point, right? So that's what you understand by a field line. So this is a mathematical way to represent a field line, that if I look at tangent to a field line at any point, then that gives me the velocity, direction of the velocity at that particular point, right? So this gives me a mathematical way to represent my field line. So this is the equation for a field line. Now, if I do the same problem in 3 dimensions, I can write the equation for my field line like this. So a field line is something that satisfies an equation of this kind, right? Just remember this, because I'm going to use this concept of field line or a streamline, right? Now, if I have a steady flow, now steady flow can be very nicely described in terms of streamlines, right? Now, what do you really mean by that the flow is steady in terms of streamlines? Is that if you look at the streamline or the slope of the streamline doesn't change with time and coincides with the path of the fluid particle at every point, right? So that means, because at every point the slope is given by del v by del t, the rate of change of slope at every point will be given by del v by del t. So steady flow would mean, in other words, that this tangent, the direction of this tangent, is not going to vary with time, and hence at all points the tangent is going to point in the direction of the flow of my fluid, right? Now I'm going to use this idea to look at this, go back and look at this equation. So let us say L cap is a unit vector that describes or that gives you the direction of the tangent to my streamline. Now, for a steady flow, what would this mean? This would mean that L cap would be in the direction of the velocity field for all times. For all times, the two will coincide, right? So that's another way to mathematically represent a steady flow. Right? So now, what I'm going to do is, so this is a vector equation I told you yesterday. Now, what am I interested in? What I'm interested in is looking at the flow of the fluid. And the flow of the fluid is described by this tangent vector. What does this mean? That this flow in general is in all directions. But if it is a steady case, so that's what I understand by a steady flow, then its direction is given by the tangent to the streamline. So I take a dot product, that is projection, because that's the only thing that I'm now interested in, is projection of this vector equation along the direction of my streamline. So now what do? I take a dot product of this vector equation. I hope you all understand that this is a vector equation. Now, what do I mean by doing L dot grad? L dot grad means that I look at the derivative or the change in the velocity field only along the streamline, right? Because at all points, it's a steady flow. At all points, the direction of the tangent to the streamline is going to give me the direction of flow of fluid. So I'm just interested in looking at the flow along the direction of the streamline. And when I do L dot del, so this is just like taking a dot product. You know, when you have a vector and when you take dot product of two vectors. So this is a unit vector, just like when you have a vector A and you have a vector A, you take its dot product with a unit vector along I cap direction. What do you get? You get its X component. You take a dot product along Y, you get its Y component. Similarly, gradient operator, you know, is a vector operator. It represents change. It measures change in quantities, right? So when I do L dot del, what does that mean? Is that I look at the component of gradient along the L direction. That is, I look at how quantities. So this operator is now going to measure what? It's going to measure change along the streamline or along the tangent to the streamline, right? But so when I take the dot product with the first quantity, what will I get? I get half del by del L of V square. But what happens to the second term? When I take the dot product of L dot with V cross curl of V, what is the direction of this vector? You know the direction of this vector. What is going to be the direction of this vector? This vector is V cross something. So this has to be in a plane perpendicular to the plane containing my vector V. But L cap is in the direction of V. So if I take a dot product of L dot V cross something, that's going to be 0. Because L is in the direction of V and this vector is in a plane perpendicular to the velocity vector. So this term is 0. And similarly on the right hand side, I get minus del by del L of W. If you want to get a physical feel of what do I mean by this, go back and just think about how I replaced W. Where did W come from? W came from writing pressure. So this is kind of measure of how the pressure changes along the direction of flow. So that's what this term represents, right? Wonderful. I have a very nice equation. I just rewrite this equation. Like this. What does this mean? This means that I'll repeat again. This represents change along the direction of flow. And there is this quantity in the bracket. What does this equation mean? This equation means that the change of this quantity along the direction of flow is 0. So what does this mean? That this quantity doesn't change. It's a quantity that is conserved, that remains same along a streamline. Okay, the motivation behind using the concept of streamline, why did I actually bring in this idea of streamline is, see, we are dealing here with a very simple concept. We are dealing here with a very simple concept of a case where my flow is a steady flow. That is where I have del V by del T equal to 0. But if somebody is interested in actually not looking at more complicated cases, I'm not going to do that. It's not, it doesn't interest us. We're not interested in that. So, but if somebody wants to do a little bit more complicated cases, you realize that it's the concept of streamline that becomes very useful, right? In such cases, we may not always be along the direction of the streamline, or you can also say it like this, that the streamlines would keep changing as you move along the flow of the fluid, right? So why did I bring this concept of streamline? Because I could have just said here, instead of defining a tangent to a streamline, I could have just said that you look at, take the dot product along the direction of flow, along the velocity vector. But that will not help you if you do a general case. Because when you do a general case, velocity field is a vector field. It becomes very complicated to deal with. On the other hand, if you look at tangents, you look at field, just like in electricity, magnetism, and other fields, this idea of field lines gives you a visual feel of what is really happening. In fluid dynamics also, you define quantity, you define this thing like a streamline, because when you will do complicated cases, if you actually do complicated flows, then the idea of streamline is going to give you a visual picture for your problem. You may not appreciate my bringing in the idea of streamline here, but let me tell you, it is actually a very useful idea. Okay, now I come back to this equation. That was a side note talking about streamlines. I come back to this equation, and this is what people were asking for yesterday, is the famous Bernoulli equation, right? This is what you call as, so if you have so what does Bernoulli's equation represent? Bernoulli's equation just represents a conserved quantity, a quantity that is conserved along the direction of flow. And let me tell you, you just look at this equation slightly carefully. You'll get a feel for what is this equation. You just multiply this equation by density throughout, rho. By the way, this was work done, specific work done. So if your rho, if you assume, you look at it for a simple case where my rho is uniform throughout my fluid, I just multiply this equation by rho. On the right hand side, I'll get rho multiplied by a constant as a constant. You see, this is nothing but conservation of energy. You have something like kinetic energy, and you have a term like work done against the pressure forces, right? And you see that Bernoulli's equation is nothing but a measure of conservation. Again, you have, so everywhere you look at these complicated equations, but if you try to just think about these complicated equations, they always represent simple physical ideas. You get the feel for those simple physical ideas only when you do simple cases, right? If you start with a complicated case, you will never be able to see something like a Bernoulli's equation. You will never be able to understand that what do you really mean by a steady flow. So what you really understand by a steady flow is that you have this quantity along the streamline which will remain constant. And why is it useful? It is useful because if you use this equation for a steady flow at two different points, you can again find the velocity field, right? You know the velocity field. you again can completely solve your problem and understand, get a solution to your Euler equation. This is nothing but a solution to your Euler equation. We started with Euler equation for a particular case, and we have again completely solved my Euler equation. I didn't include external force of gravity. It is not difficult to include force of gravity here. Yesterday we did that, if you remember. You can just include G here, right? And your equation in that case. So if your G is along the Z direction, right? Then L dot G, if you go back, well, I'll do it in little detail so that people don't feel lost. So what happens when you have G in your problem? What happens when you have G in your problem? Then your equation reads like this. Your Euler equation would read like, you'll have a value, you'll have a expression for G, or you'll have G on the right hand side in your equation along with grad of W, right? So your equation will become, in such case, you can just write your equation, rewrite your equation, Euler, it will become del V square minus V cross del cross V minus equal to minus grad of W plus I have written it. I have written it correctly. Not in the bracket. Paste. Right? Now when you will do L dot G, what would L dot G give you? What do you mean by L dot G? You are just looking at the component along the direction of flow. So that will be nothing but writing it as del G. Why? Because what is the direction of G? It is Z cap. So this is what? It's going to just give me the angle between. So when I do L dot G, I can write as G Z cap. So this is nothing but L dot Z cap times G. Both are unit vectors. If I do L dot Z cap, it is going to give me nothing but cosine of angle between L and Z. And that's what this denotes. Cosine of angle between L and Z. Right? In that case, how will this equation get modified? In that case, the equation will get modified as V square by 2 plus W plus GZ is a constant. So in presence of external field, external force of gravity, my Bernoulli's equation will become like this. Right? Okay. I can wait for a minute. Maybe look at are we considering, so there's this question, are we considering that the flow is a streamline for the volume element dV? Okay, so that's what I told you yesterday. dV is a representation of the whole volume, right? I cannot deal with the whole bulk in one go. So this is Mrudul's question, right? We are not, so you say that why are we not concerned about the rest of the volume? We are indeed concerned about the rest of the volume. This dV, this element dV is a representation of my bigger volume only. When you look at, so you are looking at just like, fine. So the thing has to be seen like this. Whenever you look at dynamics of a system, right? Whenever you look at dynamics of something, you look at, for example, when you are doing mechanics or you are doing any other problem, you have a mass at hand and you analyze how the element. So here, the object of interest, I have defined it as my volume element, this small volume element. So you can see this small volume element as the physical quantity whose dynamics I am studying, right? Ma'am, is Bernoulli's equation only for steady flow? Well, Bernoulli's equation in this form is yes, indeed, only true for steady flows. When you have a steady flow, only then you can write something like v square by 2 plus w equal to a constant. Ma'am, is that g minus gz or gk? Oh, right. So thank you for pointing that out. You're right. Yesterday, I didn't use gz cap, but I used gk cap. Right? Yeah, so z cap, I'm so sorry. Sometimes I get carried away. I start denoting the unit vectors as x cap, y cap, z cap. But yes, it is gk cap only. I'm sorry for that confusion. Ma'am, please explain L dot G part. Sure. L dot G part, as I said, what is L dot G? When I look at L dot, when I take a dot product of any quantity, dot product of any quantity is just looking at projection or component of that quantity along the direction of the other vector. So here I am looking at, since I am interested in looking at how things vary along L cap, so I look at component of G along L cap. Now, what is vector G? Vector G is G.
Geetanjali ma'am, you are on mute, so kindly.
I'm sorry,
Yes.
somebody might have muted me. When did I? I'm sorry, where did I start? From where did I missed it?
No, you can continue. You can continue, please.
Okay, I hope I was not muted for a long time. I didn't realize that. Maybe somebody else muted me. Okay, so L dot G is simply looking at the component of G along L. What will that be? So it will be magnitude of G, L dot K cap. Now when I do L dot K cap, when I do A dot B, when I look at dot product of two vectors, what is dot product of two vectors? Magnitude of two vectors multiplied by cosine of the angle between them, right? The angle between them. Now here, since the two vectors are unit vectors, their magnitude is 1. So it is just cosine of angle between them. And the cosine of angle between them is given by del z by del L. That's it. So that's what I meant by, yeah, I'm sorry if there is a mix-up of signs somewhere. Definitely, I will try to figure it out, right? Yeah, I can realize that yesterday probably there was a mix-up of signs somewhere. I'm really sorry. But I'm sure that the equation that I started with today is perfectly correct. So you can just go back. That sometimes happens when you are actually doing live writing in front. That happens in class also so many times. And when I'm doing something, I often mix up signs, right? But it is not difficult. I'm sure you can figure out where the sign, it's just a plus minus sign. I might have messed up while copying something from one equation to the other. I'm sure you can get that corrected. It will not really make a big difference to you, right? Okay, so I think I've answered most of the questions. Maybe I can take, if there are some important questions on YouTube till this point, can somebody look at those questions?
Host, please kindly read the question.
Yeah, ma'am, we'll shortly tell you the compiling the questions. We'll shortly tell you what
Okay,
questions
so
are there.
I'll proceed then, because I'm going to now erase this start. Okay, fine. So now I have done two applications of cases where I did not include any kind of dissipation, right? Any kind of dissipative forces. People have been asking
Pushpa
me
ma'am,
about.
kindly mute yourself. Pushpa ma'am, session is interrupting. Pushpa
Okay.
ma'am.
Yeah, so today now, before I include dissipative forces
Ma'am, Geetanjali ma'am, continue please.
or dissipation in my system, I'm going to define a new quantity for you. So this is going to be slightly difficult mathematics, but don't worry, I'm going to go slowly. I'm sure you will catch up, right? I'm going to define a quantity called momentum flux, right? Now, momentum of my fluid, of my unit volume, my volume element, is equal to rho times V. If I look at rate of change of momentum, rate of change of momentum will be V del rho by del T plus rho del V by del T. Right? Now let me write this equation in form of, so I'm going to use tensors. Right? Now you know, because you've been reviewing for last few days in special theory of relativity, you must have reviewed this idea that vector is nothing but a tensor of rank 1. Right? So I'm just going to write this equation using indices. Instead of putting a vector sign, I'm going to put an index. Right? So this is a vector V, which is a tensor of rank 1 in 3 dimensions. So I can take value 1, 2, 3. That's what I understand by a vector equation. If I have a vector equation is going to be true for every component of that vector. What does that mean? That this is going to be true for Vx, for Vy, for Vz. And hence I write Vi. Vi del rho by del T plus rho del Vi by del T. Right? Okay. Now let's keep this equation. Let me call this as equation number 1. I don't have the habit of putting equation numbers, but let's for some time put the equation numbers because that will help us. Now from continuity equation, what do I have? I have del rho by del T equal to. Now I will remind you, continuity equation, the way we wrote it was del rho by del T minus grad of rho, minus divergence of rho del dot rho V in vector form. Right? Now I'm going to write this equation also in a tensor form. You know this is a vector operator. So in tensor form, I can write this as a divergence and right. So what is this right hand side? Since k is repeated, that means the right hand side is actually a summation over k. K can again take value because it is in 3 dimension, 1, 2, 3. I'm not going to put this summation. So whenever you see a repeated index, summation is implied. So this is my continuity equation. Let's call it equation number 2. Now, third equation, Euler equation.
There is a question, ma'am.
You want me to take it right away?
Yeah. So the question. Sorry.
You want me to take the
Would you
question?
like to take the question? No, that's okay. Maybe you can proceed. I'll take it up.
Let me just fill this up. Then we'll.
Yeah, sure.
Okay. So again, writing Euler equation using indices, del Vi by del T equal to minus Vk, del x by del k Vi minus 1 by rho del by del xi of P, pressure. It's a task for you. You go back, look at Euler equation for 2 minutes and see if you can write this. Yeah, so in the meantime, you can give me the question. Okay, maybe I can't hear you, so we can come back to it later. Let me just proceed. So people should try to get this equation. Okay, so now I have these 3 equations in the form that I need them. Now what I'm going to do is that I'm going to go back to this equation, substitute the continuity equation. So I replace in equation 1. I'm going to use equation 2 and 3. So in equation 2, from equation 2, I replace del rho by del t. And from equation 3, which is del Vi by del t, I replace del Vi by del t in equation 1. And I write my equation as, rewrite my equation 1 as del by del t of rho Vi minus rho. You have to be very careful with the indices. Del by del xk, Vk, del by del xk, Vi. So this is the same term that I have here. And then, so I'm substituting for this del rho by del t, right? From here, right? And I get minus del, since I multiplied it by rho, this rho goes. So what do I have? Del p by del xi minus Vi del by del xk rho Vk. I've just substituted for, in this equation, for del rho by del t, right? So I have Vi times del rho by del t, which is this term, with a minus sign has come from here. So that's why this term becomes negative. And then I've substituted for rho times del V by del it. So I have del Vi by del t multiplied by rho. So I get rho with a minus sign Vk del Vi by del xk. Again with a minus sign. Rho being multiplied by this gets cancelled. I'm just left with del P by del xi. I'm going slowly because this is a little difficult. I'm going to stop soon. Now I combine the first term and the third term. Look at the first term and the third term carefully. Let me write them separately. Vk del Vi by del xk minus Vi del by del xk rho times Vk. So you see, rho Vk, Vi, Vi. So this is like the two terms from the product rule, and I can combine them and write this as, how can I write this? I can just write this as del by del xk rho Vk Vi. You open it up, you get del by del xk of rho Vk into Vi, which is this second term. Then you pull out rho Vk del by del xk of Vi, which is this term. So I'm going to combine these two terms in my equation 4 and write my equation 4. You can see it really doesn't matter whether I write it as Vi into Vk or Vk into Vi. This is a symmetric term. And I am left with this term. And I make a small mathematical trick. This is a derivative with respect to xi. I change it to xk using what I call as a Kronecker delta. You know Kronecker delta is a tensor of rank 2. Whose components do not change or remain same when you go from one frame to the other. Wonderful. Now, if I do this change, I can write my right-hand side. As del rho Vi by del T. You must see carefully, K is summed over, it's not a free index. The only free index on the left hand side is I, and the only free index on the right hand side is also I. My equation is correct. That's a very important check to verify whether your tensor equation is correct or not. So I can write the right hand side and I can write my equation. What was this equation, by the way? The left hand side measured rate of change of momentum. Rate of change of momentum. Right? Now, if you look at this carefully, this equation is just like a continuity equation. This quantity in the bracket, rho Vi Vk plus delta Ikp, is a tensor of rank 2. I call it momentum Why? Because Vi Vk is a symmetric term and delta Ik, Kronecker delta, is a symmetric tensor. Right? So rho Vi Vk plus delta Ik can be combined into a tensor, what I call as momentum flux tensor. And then I can write, I'm going to stop after this, rho Vi by del T as minus del by del Xk as this. You can still see that I still have one free index on both the sides. So this is still my vector equation, like I started with. Right? The nature of my equation doesn't change. It's just that now I'm representing it in terms of tensors. Right? It is just like a continuity equation. Why? Because you see right hand side is like divergence of a vector. Right? So pi ik del by del xk, pi ik is nothing but like divergence. And on the left hand side, you have a rate of change, just like you have in your continuity equation. And that is the reason why this is called a flux. Right? If I take a volume, if I now sum over, instead of looking at just my single element, I sum over the whole volume. So I do an integral of both the sides. Over V naught. Then again, using Gauss divergence theorem on the right hand side, because this is like del dot of a vector on the right hand side. One index is summed over, you have one free index. So this whole quantity is like, you have a divergence of a quantity. I can write the right hand side with a minus sign as pi ik dak. Where what is dak? dak is the component of your area element along the kth direction. And that is why now you can see this term as a flux. Right? You can remember from your vector calculus class in your first year that like you have when you look at electricity, you look at magnetism, everywhere you have flux, right? You have B dot dA over a closed integral. So this is like flux, and that is why this quantity is called a momentum flux. And this equation is nothing but continuity equation or conservation of flux. So you see, I started with rate of change of momentum. So what is this flux basically going to represent? Is that if I look at how momentum changes within a small volume is just like flux of the momentum flowing out through the surface of the volume that describes that element, right? So within a small element, you have momentum changing, momentum of that volume element changing, but where does that momentum go? That momentum goes as the flux that flows out. So this is nothing but conservation or continuity equation. So it's like conservation of flux or continuity equation in terms of your flux density or momentum density, right? I'm going to stop here. So today's lecture has been slightly involving, slightly mathematical. I would suggest that if you come back tomorrow to listen to my lecture, so tomorrow's lecture, I'm going to start from here. And this is the starting point for Navier-Stokes equation. I'm going to start from here, arrive at the Navier-Stokes equation, and then in the end, describe the viscosity experiment that you do in your first year, where you determine coefficient of viscosity of a system and define quantities like Reynolds number tomorrow. But this is going to be my starting point. Now, what I want to say is, since this lecture has been slightly mathematically involving, it will be useful for you to go through this before you come back tomorrow for tomorrow's lecture, right? So I think I will stop here because otherwise it will become too much for you. You should go back and try to do the analysis and try to fix my negative sign problem for me, right? Let me see if there are any questions that...
So one of the question on YouTube was that can we write entropy in terms of continuity equation?
Sorry, how did I?
Write entropy in terms of continuity equation. Is it possible? So it's talking in terms of Landau book, the book by Landau, and he's asking that can we write entropy in terms of continuity equation?
No, I'm sorry, but I don't understand what really that means, is writing entropy in terms of continuity equation. If you want to talk about conservation of entropy, right, that is how entropy changes.
Yeah, I think that is the way it should have been posed.
Yeah, but the problem at hand, the systems that we are dealing with till now are systems which are non-dissipative, for which entropy is actually remaining constant. So a continuity equation in that sense for entropy would just read ds by dt equal to 0, because my entropy is not changing with time. So I'm not sure whether you call this as continuity equation for entropy, but yes, the systems that we are dealing with are systems for which ds by dt is 0. That is, for us, the entropy is not changing with time. All the analysis that I have done.
Pushpa ma'am, can you unmute yourself?
Sorry? I am not muted.
No, ma'am. He was saying to somebody else. So, yeah, thank you. If there were no more questions on YouTube, and I think this is, Yeah, if there are any more questions on the chat box, we'll have it. Just
Okay, so somebody has asked, entropy is not conserved.
yes.
I'm dealing with cases where indeed my process is an isentropic process, because see, what you really understand by a process which is an isentropic process is an adiabatic process. There is no exchange of heat or loss of heat in terms of physics. That also means something very important, is that all the processes that I'm talking about are reversible in time. So if I look at the fluid flowing in one direction with time, and if I reverse the time, I can actually reverse my process. That's what I understand by reversibility in time. So the kind of processes that I am till now concentrating on are cases where ds by dt is 0, where entropy, my processes are still isentropic processes. Somebody has asked, repeat what is dak. Okay, so dak is just, if you go back and you look at how you write down the equation, you use Gauss divergence theorem for any vector is just b dot da. Let me write it a little big here. I hope I can erase this. So this is somebody's question, what is dak? So if you look at Gauss divergence theorem, in Gauss divergence theorem for any vector b, you can write for that vector b like this. Now when you do a dot product, what do you mean? That this is nothing but vector element, or you look at component of b along the area element. So there is a direction, a sense of direction that you associate with an area element, which is normally given by the normal to the surface, right? So it's just writing this thing in tensor form, right? This is just writing this thing in tensor form. When you have pi I k dak, it is just writing momentum dot da. That is flux of momentum along the direction of, so dak is just component, is a component of my area vector. That's what I mean by dak. Ma'am, please tell once, how did we write the cross product term from Euler equation tensorially? No, there was no cross product term. There was no cross product term. I got rid of the cross product term before starting this. There is no cross product term in the Euler equation. I think, Himani, you have mixed up. You are mixed up somewhere. There was no cross product term. Ma'am, is it so that if we take curl of Euler equation, we only get divergence less terms of velocity on solving it? No, that's not right. That is just one particular solution to that equation, where you look at you are getting quantities by taking a cross product. You are just looking at the Euler equation in a different way, right? No, I'm not doing that. No. I think I have kind of sorted out all questions on Q&A box. If there are any other questions from YouTube you want me to answer, or maybe then.
So the YouTube questions have been taken, ma'am. So this was such an enriching talk. We thank you a lot. And now I request Dr. Pushpa Bindal, ma'am, to please come and thank Dr. Geetanjali.
So thank you so much, Dr. Geetanjali. It was such a involved and such an informative talk. Thanks for taking so much of pain for the students. It was really good. We thank from the core of our heart. Thanks a lot. And we look forward to your next talk. So I think that should be the end of the session for the day. Is that right, Nitu?
Yeah. Thank you, ma'am. So I would suggest everybody that today's talk was a little mathematical. I will again insist, please go back and go through the whole analysis before you come back tomorrow. Thank you.
Thanks again, Dr. Geetanjali. It was such a lovely talk.
Thank you.
Okay.
Thank you, everyone.
Thank you, everyone.
We'll be meeting tomorrow again in the next session. Thank you. The attendance link has been shared. The participants are requested to please fill the attendance form.